today's video, we are going to go over the gradient vector as well as the directional derivative. Now remember, a vector is a direction, and in order to find this direction, we're going to use del, which is the upside down triangle, of f of x of y, which equals the partial derivative of x, and then the partial derivative of y, which is going to be our I and j values, or, our x and y in Cartesian. Now our next thing we need to know is how to do a unit vector, which if you recall is just getting a vector. For example, if we get 4i plus 5j, same as 4, 5, and we put it over its magnitude or length, which in this case would be 4 squared plus 5 squared under a square root, or the square root of 16 plus 25, which equals the square root of 41. And then you would just put 4 over square root of 41, comma 5 over square root of 41, which would be your unit vector. Now the reason we need the unit vector is because we're required to use the gradient vector and the unit vector to find the directional derivative, which is just the dot product of the two. So that is the introduction for gradient vector and directional derivative. Now, one thing I wanted to mention here is sometimes you will be given the unit vector, so you don't have to normalize the vector. But if you are given a vector, like let's say the 4 and the 5 I used earlier, make sure you normalize it. And what I mean by normalize it is just turn it into a unit vector and then do the dot product with the gradient vector. Because sometimes they'll just give you the vector or the unit vector. It depends. Now, our first problem is to find the directional derivative of f of x of y, which equals x squared y cubed at point 1, 2 in the direction of the vector v equals 3i plus 4j. Now to simplify all of these words into 4 easy steps, you have to remember that the first step is to find the gradient vector. The second step is to evaluate at the point, which in this problem is point 1, 2. The third is to find the unit vector. And the fourth is to do the dot product of the gradient and the unit vector. So we'll turn this into a checklist real quick, and I'll put it to the side. Now remember, to find the gradient is the equivalent of taking the partial derivative of x and the partial derivative of y and putting it into I and j form. And given our f of x of y being x squared y cubed, our x partial derivative becomes 2x y cubed, and our y partial derivative ends up becoming 3x squared y squared. So we can plug those values into our I and our j. So since we did find the gradient, we could check it off our list. Now our second step is to evaluate at the point. So in this case, our point says it's 1, 2. So all we do is rewrite our gradient into f of 1, 2 and plug in our x as 1 and our y as 2. And again, all I'm doing is plugging our x's and y's in correlation with the 1 and the 2. Now we can simplify this much further into 2 times 2 cubed, which is 8, comma 3 times 1 squared, which is 3, and then 2 squared, which is 4. And finally, our gradient vector at 1, 2 becomes 16, 12. And again, you can always put it into a different form, such as 16i plus 12j. Same exact thing. So we did our second step, which was to evaluate at a point, which in this case, our point was 1, 2. Now our third step is to find the unit vector. And since we're given the direction of the vector v equals 3i plus 4j, which I'll write down here, we have to turn this into a unit vector, which was what I was saying earlier with normalizing the vector given. Now again, sometimes you can be given the unit vector itself on the test, but just remember, if you are given a vector, normalize it or turn it into a unit vector. Same thing. So remember, our formula is the vector over its length, and plugging into this formula, this becomes 3i plus 4j over 3 squared plus 4 squared under a square root, which eventually becomes 3i over 5, since this eventually becomes the square root of 25, comma 4j under 5 as well. And that is our unit vector. So we can check that part off our list over here. Now our last step is to find the dot product of our gradient vector and our unit vector. So our directional derivative equals the gradient times the unit vector. And in this case, over here, our gradient was 16, 12, dot product with our unit vector, which is 3 over 5i, or just 3 over 5, comma 4 over 5j, or just 4 over 5, because I'm going to put it into the vector brackets. And if you don't recall how to do dot product, it's just the i's multiplied plus the j's multiplied, which in this case is 16 times 3 over 5 plus 12 times 4 over 5. Now these two come out to be 9.6 and 9.6, which results our final answer to be 19.2. And that is our directional derivative. And we can finally check that off our list. So in summary, we found the gradient vector by finding the partial derivatives of x and y and putting it into I and j. We evaluated it at the point, which was in this case 1, 2. We found our unit vector, which was 3/5 I, 4/5 j. And then we found the dot product of our gradient evaluated at the point and the unit vector. Now that we know it's not that bad, let's just find the directional derivative of h of p of q, which equals p e to the q at the point 2, 0 in the direction of the vector v equals I plus j. So this time our gradient vector is in terms of h, p, q, which literally changes nothing. This is the same procedure, which if we find the partial derivative of p, we get e to the q, and then taking the partial derivative of q, we get p e to the q. Since taking the derivative in this case changes nothing because it's exponential, so easy peasy, we found the gradient vector. Next, we evaluate this gradient vector at the point given, which is 2, 0. So plugging 2 into p, we get 2e to the q, which in this case is 0. And then same here, it's just e to the 0. And simplifying further, we know e to the 0 is just 1, so this becomes 1, and then 2 times 1, which we just say 2. So we could check that off our list. Now the next step is to find the unit vector of I plus j, which is the exact same as just saying 1, 1 in component form over 1 plus 1 each squared under a square root, which then becomes 1 over the square root of 2, 1 over the square root of 2, which is our unit vector. And so then we can check step 3 off our list. And our last step is to find the directional derivative, which is the same as del h 2o under the dot product 1 over square root of 2, 1 over square root of 2. And sorry, I forgot to put a square root under here, which we know our del of h of 2o is the same as 1, 2 as found over here. Dot product with 1 over square root of 2, 1 over square root of 2, which then gives us the directional derivative of 1 times 1 over square root of 2 plus 2 times 1 over square root of 2, further simplifying into 3 over the square root of 2, which we can simplify even further since we don't want our radical in the denominator. And a quick refresh on how to do that is just multiply the denominator over its own self. And the reason we do this is because it cancels out the square roots on the denominator. So then it becomes 3 times the square root of 2 over just 2. And that is our final answer. Good luck on your test.